In the last class, we started discussing about varieties of things about chemical shift. I introduced to you about chemical shift, how do we calculate in ppm, what is the reference we use for different nuclei. I said for proton, carbon and silicon, tetramethylsilane is the reference which is always used. Measure the resonating frequency of a particular peak from your sample with respect to the reference which is set as 0 frequency, divided this by spectrometer frequency. The value you are going to get is nothing but the chemical shift expressed in parts per million. The advantage of expressing in parts per million is it removes field dependency. That means you record the spectrum in any spectrometer, when you express its value in ppm, it remains same. For example, if I say CHCl3 comes at 7.2 ppm in 400 megahertz, whether you go to 600 megahertz, 800 megahertz, 1000 megahertz, its chemical shift is always 7.2 ppm, there is no change. And then when we have a value, when you get the chemical shift in ppm for a particular spectrometer, we can convert into frequency. How do you convert into frequency? By multiplying the ppm value by the resonating frequency of particular nuclei. For example, in a given spectrometer, different nuclei will have different resonating frequencies. That is what we have been discussing from the first class. Now I know in 800 megahertz, nitrogen comes at 80 megahertz, 10 times lower gamma. What we can do is, if I know the resonating frequency or chemical shift of nitrogen 15 in a particular peak, let us say 100 ppm, if I have to express in frequency, simply I have to multiply this 80 by resonating frequency of 100 for nitrogen 15 in 800 megahertz spectrometer. If I know, let us say 8000 is the frequency for nitrogen 15 in 80 megahertz, in 800 megahertz spectrometer, its resonating frequency is 80, divide the 8000 by 80, which is 100 ppm is the value. So like that, for any given nuclei, you know how to convert frequency to ppm and vice versa. And I also mentioned about the concept of high field and low field. When you go from left to right in the spectrometer, I mean the spectrum scale, left to right is always going to the high field, lower frequency, higher shielding. Okay. So this is what the concept we said. When you go from right to left, this concept gets reversed, which is less shielded, lower frequency, higher frequency and then lower ppm. These are the concepts which we discussed. Now we will go further and understand a bit more about chemical shifts and how chemical shifts come for different nuclei. What are the factors which governs chemical shift? Those things we will try to understand today. And chemical shift and its value, how is it field dependent? That is what we will understand. Of course, chemical shift is field dependent and its spectral dispersion is better with higher and higher magnetic field. That means higher and higher frequency spectrometer. If you go, the spectral dispersion becomes better. That means the peaks start spreading more and more. Let us say there are two peaks which are close by like this. In some frequency, let us say 100 megahertz. If you go to 1000 megahertz, it will become like this, well separated. This is the advantage. That means as you go to higher and higher frequency, the resonating frequency, the chemical shift, what happens? There is a spreading. This frequency starts spreading more and more, dispersion becomes better and better. And let us say what happens to the chemical shift scale. In a 200 megahertz chemical shift range of proton is 0 to 10 ppm. If I consider the total frequency is 2000 hertz. We already know how to convert 10 ppm for in 200 megahertz is 2000 hertz. If I go to a 400 megahertz spectrometer, same 0 to 10 ppm range is 4000 hertz, because a 400 megahertz. See, the dispersion became better now. Go to 600 megahertz, the same 0 to 10 ppm becomes 6000 hertz. What is happening? The spectrum which gets crowded at lower frequency start becoming better and better, gets dispersion more and more as you go to higher and higher frequency. This is the reason where chemical shift, when they even express in frequency, it keeps becoming more and more, spread becomes more better and better, that corresponds to better and better resolution, and your analysis becomes much better as you go to higher frequency spectrometer because of better resolution. And we will consider chemical shift in frequency in ppm scales, that is what we have been discussing. In ppm scale it will not change, but in frequency scale it changes. I will show you like this. For example, in a ppm scale I have 3 peaks on a 200 megahertz spectrometer, which is coming at 1 ppm, 3 ppm and 6 ppm. 3 peaks are there. Recorded 400 megahertz remains same, 1, 3 and 6 it will not change. Go to 600 megahertz same, go to 800 megahertz. In ppm scale it remains unaltered when expressed in ppm, it always comes at the same ppm in any spectrometer. Go to now frequency scale. In 200 megahertz 1 ppm is 200, 3 ppm is 600, 6 ppm is 1200. Go to 400 megahertz, see the spreading is becoming better. Now 1 ppm in 400 is 400, this 3 ppm is 1200 and 6 ppm is 2400 hertz. Go to 600 even become better, 800 even better. See, this is the dispersion. When chemical shift there is a field dependency is there. When you express in frequency and when you go to higher and higher magnetic field you see better and better dispersion. There is a lot of frequency in when you express in frequency scale there is a lot of field dependency. Okay. Just to show you in the number, let us say I have given some molecule which are different functional groups like this X, Y and Z. I want to measure its chemical shift in ppm. At 400 megahertz it comes to ppm, the functional group X could be CA, 3A, whatever it is. Then at 600 same, 800 also same. You go to another functional group instead of CA3, let us say benzene group or some other CH group which comes at 4.5 at 400 remains same on all the spectrometer. Functional group let us say OH or NH is there, comes at 7 ppm remains same in all the 3 spectrometers. On the other hand, I am expressing the same functional group in frequencies 400 megahertz it is at 800, 600 megahertz 1200 and 800 megahertz at 1600 because I express in 2 ppm. 2 ppm is 8600, 1200 is 400. Like that for different functional groups the frequencies are different. This is this table you should remember always. Again I gave this example to make sure that chemical shift when expressed in ppm remains invariant with respect to the spectrometer frequency. Okay. And of course, when you measure the chemical shift for any given molecule, every peak for every functional group over the decades, over several years, several decades, lot of research has been done and people have identified ranges for different chemical shifts for different functional groups. For example, it is like a fingerprinting of the molecule for a particular functional group. If I say there is one particular peak coming in this region, this corresponds to CA3, a peak is coming maybe somewhere here, I can say it is because of benzene, somewhere it is here CH2 group is there, or somewhere here I can say some other functional group is there. Like that more or less it has been tabulated. Over the years different functional groups where it comes in a scale of 0 to 10 ppm or 12 ppm has been by and large demarcated. It is like telling different frequencies have a different radio. For example, there is a frequency here which comes at Mysore, which comes at Dharwad, it comes at Bangalore, different radio frequencies, but frequency is constant. Similarly, the range of frequencies for functional groups are constant, but it is not a dogma, it can vary. By and large it is only a guideline for you to start the analysis. Ranges are known more or less. Of course, with respect to your molecule, depending upon the functional group surrounding a given functional group, what other groups are nearby, how the charge density is distributed at the site of the nucleus, your chemical shifts can slightly vary, but you can start this as a starting point for the analysis. Okay, when you go to NMR in the solution state, for solute of interest normally it is dissolved in a solvent, deuterated solvent which is always used. We always have to use a deuterated solvent so that you have to fix the field for locking, so the field will not drift. The field start changing, your resonating frequency keeps changing. This of course I discussed in one of the classes previous courses about field frequency lock etc. By using this deuterated solvent at a particular frequency where deuterium resonates in a given spectrometer, I can fix the field by electronics, then field will not move. then I can record the spectrum of proton and others, because deuterium frequency will not interfere in the proton resonating frequency. That is what we can do. So, we take the samples in NMR tubes like this, dissolve in some deuterated solvents, in which it your organic solvent in your molecule dissolves, or D2 or whatever it is, and then we can record the spectrum. So, common deuterated solvent normally used are acetic acid, acetone, acetonitrile, benzene, all these are commonly used solvents, and each of them have a certain resonating frequency for the solvent, because remember it is not 100% deuterated solvent. It's even then, if there is always for certain percentage of protonated solvent present. For example, if of acetic acid, it is not 100% deuterated, little bit of protonated compound will be there, then it gives rise to CH3 acetic acid COOH, CH3 groups comes here and COOH groups comes at 11.6. For example, if I take benzene, it can come at 7.2, chloroform comes around 7.25, like that different solvents, by and large we know where it comes, protonated part of that deuterated solvent where it comes. And then similarly for carbon 13 also we have a range of chemical shifts. Incidentally, what happens is most of the solvents generally will absorb moisture from the atmosphere. There will be a residual water peak here, which where it comes also I have written. For example, if I have a benzene, the residual water peak comes at 0.4 ppm. If I have dimethyl sulfoxide DMSO as a solvent, residual water peak comes at 3.3 ppm. Like that, by and large this information is available in this table, so that we know where the solvent peak is there, where the impurity peak or residual water peak is there. Apart from that, we can start interpreting the spectrum of your molecule. So, these are the chemical shift ranges of the protons. For example, over the years this has been tabulated, as I told you. For if I have a peak from 0 to 2 ppm, I can conclude it must be CH3C group. If I have a peak here somewhere here, I can say aromatic NH is there. If I say I am going to get a peak around 7 ppm, it could be aromatic, benzene phenyl group must be there. I can say this is the methylene region, this is the methane proton, this is methyl region, like that more or less ranges have been classified. Please note there is a range here, it is not a fixed value. This is also a guideline. For example, a CH3 peak which is here can come here also, depending upon the environment where it is situated in the molecule. So, these are all the guidelines we have for different nuclei. For example, carbon 13 we have range of chemical shifts for different functional groups present in the molecule. Same thing for fluorine also. So, all these things have been tabulated over the years, research has been done, and we know where this chemical shift for different nuclei will come. And you can start looking at a fluorine spectrum. If you have a CF3 group, generally you should come from 0 to let us say minus 52 minus 75 ppm, start looking at a peak there, then this could be the starting point to say there may be a CF3 group present. Like that we have to start analyzing the spectrum. That is a starting point. All these things are the starting points for the interpretation of the NMR spectrum. Now, we will say these are all the guidelines. How did we arrive at these guidelines? What are the factors which contribute to the shielding or to the chemical shifts? There are several factors. Basically, it has been divided into three parts. One is diamagnetic contribution, other is paramagnetic contribution, and the third is from the neighboring groups. The diamagnetic contribution comes mainly because of the electrons immediately surrounding the nucleus, that is s orbitals, which opposes the main magnetic field P naught, and paramagnetic component part comes because of electrons in p orbitals or other subsequent other bonds. It adds to main magnetic field. Remember, diamagnetic part opposes the main magnetic field, paramagnetic component adds to that, and generally it has a little contribution in proton, it has a contribution to other nuclei. And also there is because of the neighboring group where it is situated. What is that neighboring group? Whether it is electron donating group or electron withdrawing group, based on that all these are all factors which can add or subtract. All these factors, many factors will be there, there is not one single factor. The neighboring groups, what it is contributing, how it is contributing, whether it adds to the particular shielding or de-shielding, based on that we can arrive at the chemical shift values. These are all the factors which contribute for the total shielding at the site of the given nucleus. And these are the factors which affects chemical shift. One is the steric factor, which we all know, steric effect, resonance effect which is there when the resonance is going on, where it is coming, whether you are sitting here or here. Based on that, you know whether it is shielded or de-shielded. Conjugation is there, hyperconjugation. Heavy atom effect, that can also give rise to shielding or shifting of the peak either to high field or low field. If there is a delocalization in the aromatic, if there is a substitution here, whether it is a proton donating group, electron donating group or electron withdrawing group, based on that we can also arrive at chemical shifts. This is because of delocalization in aromatics. There is also ring current effect which is going on. Benzene, if I have a phenyl ring, anisotropic effect because every bond is inherently anisotropic. How the charge is distributed generally from the center of the bond to the end, there is, you can draw a cone like this, especially for CH groups, CH2 groups and CH3 groups, and depending upon whether the proton is situated here or here, it is shielded. For example, in the ethylene groups like this, if it is situated here and here, it is de-shielded. Like that, all these factors are there. Lot of information is available in the books. These are all the factors, many of them contribute for the shielding or de-shielding. We will take one or two examples. See, it is impossible to cover everything. Numerous examples are there, numerous factors are there which contribute for the chemical shift, but one or two examples we will take it. For what is the effect of electronegativity? That we will understand. Higher the electronegativity, electron density, lower is the resonating frequency. That is what I said. Now we will consider methyl group, methane. Methane is CH4. If I take the spectrum of methane, its electronegativity in the Millikan scale is 2.1 and its resonating frequency in proton is 0.23 ppm, that is the chemical shift of methane is 0.23, in some books say 0.24, does not matter, around this value is the ppm value, chemical shift of methane. Now I am going to do knock off one of the protons and put an iodine here. Iodine is electronegative, then its electron density is 2.5 and already from 0.23 it moved to 1.98 ppm. So that means it moved towards the lower frequency, I am sorry, lower field, okay. And if you go to, instead of iodine I put bromine, it is more electronegative than iodine. Already you see the chemical shift moved further downfield. Instead of bromine I put chlorine further downfield, and I put fluorine instead of chlorine, then you see it comes at 4.3. Look at it, 0.23 was in methane. Just by replacing one of the hydrogen's protons by a different electronegative atom, I can move this peak from left to right to some other value. This is the effect of electronegativity on the chemical shift. This will be seen, this is the inductive effect, which is seen because the inductive effect is transmitted through bonds in a molecule like this, for example nitropropane. Nitropropane has 3 different groups, chemically inequivalent. One is CH3, CH2 and CH2NO2. There are 3 groups. CH3 comes at the high field, that is more shielded, that is what I said in the last class or before last class. CH3 is more shielded than CH2, then CH3 will come, but this CH2 comes even downfield because it is attached to NO2 group. As a consequence, it comes even further downfield. So this is CH2 attached in between CH3 and CH2, this is CH3 and this is CH2 attached to NO2. Very easily with a chemical knowledge of functional group, whether the electronegative group is there and how the inductive effect is there, how this is transmitted through bonds, I can start making the assignment with certain knowledge of chemistry. This is what it is. And if I have different groups, the inductive effect can be not only for the molecule as a whole, even for a small group. NO2 can have an inductive effect, OH, SH, NH2, all these things may have an inductive effect. I have a molecule, I showed you, instead of replacing one of the protons in the methane by a electronegative atom, I will do one thing, I keep on lengthening the molecule, remove one of the hydrogen, put CH3 group, remove another, in between put another CH2 and make CH3. I keep on lengthening the molecules. Proton which methane which comes at 0.23 or 0.24, now as soon as I added one more CH2 group, it comes at 0.8 ppm, it moves downfield. I lengthen the molecule by adding one more CH2, it moved even further downfield. So the lengthening of the carbon chain also decreases the shielding. So, when they decreases the shielding, the peak moves towards downfield, and de-shielding it becomes more and more with more number of electronegative atoms. If the electronegative atoms are more at a particular site, then de-shielding is higher. I take the example of CHCl3 chloroform, it comes at 7.2 ppm. There are 3 chlorine atoms here. Instead of CHCl3 I make CH2Cl2, there are 2 chlorine atoms, it already moved to the high field. Instead of CH2 I make a CH3Cl, now there is only 1 chlorine atom, it moved to the further upfield, 3.505 ppm. So, the de-shielding effect also depends upon not only lengthening the chain, but more number of depending upon number of electronegative atoms which are there at the particular site. Also you see the de-shielding decreases with increasing the distance from the electronegative atom. This is directly attached bromine to the CH2 group, it comes at 3.3 ppm. I lengthen the molecule, add a CH2 in between. So, the effect of this bromine on this CH2 is much less. So, it moves to the high field. Add one more CH2 group, the effect of this Br on this CH2 is even much less. So, it moves even high field. So, de-shielding effect decreases with increasing the distance from the electronegative atom. And as few other factors which generally contribute for the chemical shift, there are all mesomeric effects, depends upon electron withdrawing group or the electron donating group which is present. Take for example this molecule, it is ethylene. Here all the protons are equivalent, there is a perfect symmetry here. As a consequence all the 4 protons are equivalent, it gives us a single peak at 5.29 ppm. What I do is I will knock off one of the CH, one of the protons and put COCH3 group, and COCH3 is a electron withdrawing group. When it withdraws the electron, remember what is going to happen, these 2 protons move to the downfield, this ppm value increased, went to the higher frequency side downfield. So, this what happens, it is because of mesomeric effect. On the other hand, instead of putting this group COCH3, I can put OCH3. What is OCH3? It is not electron withdrawing, now it is electron donating group, it donates electrons. As a consequence what happens, see it moves to the high field. Now it is not shielding, it is more shielded, not de-shielding, it is more shielded. So, it goes to the high field region. This is what happens depending upon whether you have an electron donating group or a electron withdrawing group. These are called mesomeric effect. They also contribute significantly for the chemical shift ranges. So, basically you look at it, there is a generic chemical shift range. If I consider a phenyl group, benzene group, benzene groups generally it comes in the region of 7 to 8 ppm, that is the generic region for the phenyl groups. If you attach electron poor group to the ortho position, electron poor group for example nitrogen or CO like that, or electron rich group like containing O or N, then what happens, the ortho protons moves downfield in this case, and paraproton will move toward this side. Similarly, see this is ortho and para, this should be meta I think. Okay. Similarly, if I have this one, it changes depending upon which is the functional group that you have, whether it is ortho, whether it is electron donating or electron withdrawing, the peak ortho, especially the effect is seen on the ortho position and in the para position. Meta position has a different effect. I can show you by an example like this. This is a benzene, let us say it is coming at 7.3, it should be 7.27 or 28. Some people have different values, does not matter, small change. Instead of proton here I put a CH3 group, then it becomes a toluene. Toluene is electron donating, methyl group is electron donating group. Look at it, which was 7.3 here, all these protons, it moved to 7.06, especially you see the effect is seen in ortho and para position, but in meta position is slightly lower. This is because of mesomeric effect again. In the RMA, instead of CH3 I put NH2. What happens in the NH2 is the electron withdrawing group, Now what is happening, look at it, the chemical shift is 7.3, it moves to the high field compared to benzene. Put nitro group instead of NH2, it is strongly electron withdrawing group, then aromatic ring will be replaced with electron poor relative to benzene, and the aromatic protons are de-shielded here. This is what happens. If I put methoxy is another thing, it is strongly electron donating group, look at it, ortho and especially para protons move to high field compared to normal benzene generic value. These are all less affected, especially meta, only ortho and para are more affected, significantly affected. So proton chemical shift trends in few monosubstituted benzene, if you look at it, I take benzonitrile, proton NMR if I take, delta ortho is higher field, more than the chemical shift is larger for this than this than this. If I take benzaldehyde, ortho proton chemical shift value is larger than para than meta. And if I take electron withdrawing group like aniline, the meta proton has more than para and ortho. This is all the substituted benzenes, some trends about the chemical shifts, especially ortho and para positions and the meta positions. This is what we need to understand. And one more important effect is the ring current effect in aromatics, especially if I consider benzene phenyl groups, the ring current will be there, electrons will be circulating going like this, as a consequence it produces a field perpendicular to the plane of the ring like this. This is the B0 position. See then what will happen, the protons situated above and below the plane are always shielded, proton in the plane of the ring are de-shielded. It is all because of ring current effect, the charges starts going like this. So as a consequence what happens, here it gets added up above and below the plane of the benzene ring, but in the plane of the ring, in its plane it always gets de-shielded. This is what happens like this. The protons sitting on the plane of the ring are de-shielded, lying above and below are always shielded. This is the reason why all these protons of benzene are coming between 78 ppm, not 69, 78 ppm generally. We also have effect of magnetic anisotropy. This, look at this type of molecule, there is a magnetic anisotropy coming into the picture. The protons which are inside of this ring comes at minus 14 ppm, it is highly shielded, and whereas the peripheral protons are highly de-shielded. Same thing if you look at aniline, the protons which are integrated inside this ring are shielded, whereas it comes at minus 2.99 ppm. I told you there are few examples where peaks can go even beyond TMS, more shielded. This is what happens, the protons which are inside goes to very high field beyond TMS up to minus 3 ppm, whereas the peripheral protons are de-shielded, comes at 9.2 ppm, more downfield, this goes more high field. These are all the effects which we can see, okay. And the charge distribution, especially if you consider CH, for example CH group, CH2 group and CH3 group, acetylene group or ethylene group, we have a form of, we can see a sort of a cone. Inherently all these bonds are inherently anisotropic. From the center of the bond, if you start drawing how the charge is distributed, you can draw a cone. For example, if I have a C single bond C molecule in ethylene groups like this, especially aliphatics, and the protons which are situated in the cone are de-shielded, protons which are situated outside this cone are shielded. This is an example when you have a molecule with a CC single bond like this. If I see double bond C, double bond, again same, protons, we have two cones like this from the center of the bond, protons situated inside the cone are de-shielded, above and below are shielded. On the other hand, look at a triple bond like acetylene, you take an example. Here in this cone protons are shielded, converse of this single bond and double bond. Within the cone, if the protons are situated, they are shielded, and above and below this triple bond the protons are de-shielded. This is something strange. This is a thing which is observed, especially when you have acetylenic proton. If you look at the acetylene proton, which actually is more shielded. Okay, this is what I just wanted to tell you. A lot of examples I gave about the chemical shifts. Too many things we can discuss, lot of things are there. It is a ocean, NMR spectroscopy is a ocean. There is no end for it. We can start discussing even chemical shift alone for several hours, lot of example, lot of molecules we can take, and what are the effects of different substituents and different regions we can discuss a lot. But there is no reason to go further. I have given you the basically idea about how we can get the chemical shift in this class, and we discussed a lot about varieties of factors which affect chemical shifts, starting from let us say diamagnetic contribution, paramagnetic contribution, contributions coming because of the neighboring group. And I also told you about how do we convert ppm to frequency, frequency to ppm, what will happen for the field dependence of the chemical shift at different frequency magnetic field. When the expression ppm it remains same, when expression frequency that changes linearly, there is a linear dependence that we observed. As a consequence, higher and higher frequency, if you go to high frequency spectrometers, there is a dispersion in the chemical shift. That is what also we saw. And how many, we took several examples of the factors which contribute to the chemical shift, especially both for shielding and de-shielding. We took the example of molecule containing different halogens. What happens as the electronegativity changes from iodine, chlorine, bromine and fluorine, how the peak starts shifting to the downfield. We took the example of an electron donating group, mesomeric effect, electron withdrawing group. We saw the effect of that, how peaks will move to high field or low field depending upon whether we have a donating group or a withdrawing group. Similarly, we have aromatics if it is there, especially the delocalization of the aromatics causes some effect. Then the more effect is seen in the orthoproton and the paraproton than the metaproton. Whatever the effect we see for ortho and metaproton for electron donating group, if it is present, converse is the case if it is the electron withdrawing group. More effect will be seen on the meta than on the ortho and para. And then we took the example of some of the cones like single bond, double bond, triple bond, how the charge distribution is expressed as a cone like this when you draw the charge distribution, and especially when you have acetylene group like this. I said it is difference is for single bond and double bond like this, the protons which are situated within the cone get de-shielded and outside the cone it gets shielded. Converse is the case for the acetylene group. So these are the general example, and I said about magnetic anisotropy like example of aniline and others I gave. Sometimes you can get an example where it is so shielded it can go beyond TMS to some value. So many factors contribute to chemical shifts. By experience you should know what are the factors which are contributing in a given molecule, and we can start interpreting and analyze the spectrum. So this is all about chemical shift. In the next class we will discuss more about another interaction parameter which is scalar coupling. So I will stop at this. Thank you very much.